Hello and welcome to the Emberhart podcast. I am Mikko and this is episode 10 of season 2. We are talking about board games and probabilities. So let us waste no more time and jump right into our discussion. Here we go. Probable payouts. Rolling the dice in Monopoly and life. Dear Amelia Emberhart, last weekend, as you sat around the Monopoly board, eager to collect rent from your favorite properties, did you think about the dice you rolled? It seems simple. 2 dice, some spaces to move forward, and your next destination in the game. But did you notice how lucky your sister appeared to be? She had houses built in just right locations when you happened to land there. There is a secret behind those dice, and today we are diving into it. I believe that half the people who play games with 2 dice have no idea what the probabilities in play are. Of the other half, most have only a vague understanding of what is going on. Perhaps 1 in 10 has the curiosity to think about it enough to truly understand it. It is not rocket science, just basic math. If you roll a single die, understanding the probabilities is straightforward. Each side has an equal chance of landing face up, 1 in 6, or about 17%. Rolling a 4, for example, is no more likely than rolling a 1 or a 6. Easy enough. Now let us introduce a second die, and things quickly get more complex. You are no longer dealing with just 6 outcomes. You are juggling 36 possible combinations. And as it turns out, not all outcomes are created equal. When rolling 2 dice, the sum of the numbers can range from 2, 1 plus 1, to 12, 6 plus 6. However, some sums are much more likely to appear than others because multiple combinations can produce them. Let us take a couple of examples. To roll a 7, you can achieve it with these combinations: 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. That is 6 combinations out of 36, giving a probability of 1 in 6, or about 16.7%. To roll an 11, only 2 combinations work: 5 and 6, and 6 and 5. This means the probability is 2 in 36, or about 5.6%. This difference in probabilities is why rolling a 7 feels so common, while rolling an 11 seems like a special event. And to roll a 12, you are right. There is only one combination, 6 and 6, with a probability of 1 in 36, or about 2.8%. Common biases that distort probability understanding. Why do people get this wrong? Why are so many confused by these probabilities? A few basic biases might play a role. Equal likelihood bias. People often assume all outcomes are equally likely. They might think that every sum from 2 to 12 has the same chance of appearing, much like with the single die. While this feels intuitive, it is completely incorrect when rolling 2 dice. Overlooking combinations. Many people do not realize that multiple combinations can lead to the same sum. For example, the sum of 7 has 6 possible combinations, while 11 has only 2. This difference drives probabilities. The gambler's fallacy. This is the belief that if an outcome has not occurred for a while, it is due. For instance, someone might think they are bound to roll a 12 soon because they have rolled other sums several times. In reality, every roll is independent and the probabilities reset each time. Poor intuition about ratios. Even when people know that 7 is more likely than 11, they often underestimate how much more likely it is. They might imagine it happens a bit more often, when in fact it is 3 times as common. Applying probability understanding to everyday life. Weather forecasts. Can we use this understanding of probabilities in everyday life? Are we just talking about games, or does this have broader importance? Of course it does. Let us explore probabilities using a simple real-world example: weather forecasts. Imagine the forecast says 30% chance of rain in the morning and 40% chance of rain in the afternoon. At first glance, you might think there is a 70% chance it will rain at some point during the day, right? But probabilities do not work that way. These events are independent, meaning they do not affect each other. To calculate the overall chance of rain during the day, we need to find the chance it will not rain during either period, then subtract that from 100%. The probability it will not rain in the morning is 100% minus 30%, 70%. The probability it will not rain in the afternoon is 100% minus 40%, 60%. To find the chance it will not rain at all, we will multiply these probabilities. 70% times 60% is 42%. This means there is a 42% chance it will not rain at all and a 58% chance it will rain at some point. Like with dice, probabilities in real life often behave in ways that are not intuitive. Understanding them can help you make clearer, more logical decisions. In Monopoly, the roll of the dice determines how far you move. Sums like 7 are more likely to appear, meaning spaces located 7 steps ahead of your current position are the most likely places to land on your next turn. Properties in these locations are like prime real estate. Was your system strategically buying houses in these high-traffic spots? So, the next time you roll the dice, whether in game or in life, remember the lesson of the 7 and the 11. Probability is not just a number. It is a tool to see the world more clearly and act with greater confidence. This is your moment. Take command and show us the path. And that's a wrap. Thanks for listening, and I will see you next week.